Hey everybody, welcome back to EM378 SI. Today we're going to go over problem 8.4. We're starting laminar versus turbulent flow. Again, if you got questions, if you want to see more problems, WebEx. Um, I don't do everything. I don't do all the content that I prepared on here. If you want to see everything and get more review, find me on WebEx. That way, um, yeah, if you have questions, you can ask those. If you want to see more examples, I have them up there. Um, yep, we're trying to encourage as much participation as we can in these WebEx meetings. Um, yeah, if you think this YouTube channel is helpful, you should try the WebEx. You know what I'm saying? Anyway, and again, you can get to the WebEx link uh, through the SI website. So just in Google, type in ISU or Iowa State SI, hit enter, go to our website, find me under EM378, and we should be good. All right, let's get into this problem. So we have air at 200 degrees Fahrenheit flowing in a standard atmospheric pressure in a pipe at a rate of 0.08 pounds per second. Determine the minimum diameter allowed if the flow is to be laminar. And remember, with laminar, Reynolds number, our largest Reynolds number for laminar flow is 2100. So keep that in mind. So we're looking for, you're going to see this over and over, this Reynolds number here, to be 2100 to find this diameter that we're looking for, right? And that diameter is this here. Alrighty. So what we're looking for, or what we're given, is this 0.08 pounds per second. And remember, that is a mass flow, or m dot. And we got to ask ourselves, how do we get this information here into terms of a diameter that we can use over here? Because we're given a velocity, but how do we get, like, the density and the viscosity we can find other ways, but this velocity here we're going to need from this mass flow rate. So if you remember your continuity equation, velocity is equal to flow over the area. Q over, and here our area, since it's a pipe, it's going to be circular. So there's your area there. We can substitute that into our Reynolds number here. So we get Reynolds number 2100 is equal to our density times, this is our new velocity, this expression here, Q over pi over 4 times diameter squared times the diameter over mu 2100. I wrote that twice, but you get the idea. All right. And this can be simplified a little bit, and we can rearrange stuff. And say our Q is equal to yeah. All right, so Q is equal to 2100 times pi mu d over 4 rho. We'll come back up here once we have more of the values that we're looking for. This right here, anyway, don't worry about it. So we want to get this Q into variables that we already have over here. Yeah, all right. Once I got lost in my notes real quick. All right, here we go. So we know that m dot is equal to gamma times q, so 0.08 is equal to gamma times q, and gamma is gravity times rho q. All right, and we know that rho, if you remember our ideal gas law, is going to be this here, where this is the density of our fluid, the pressure of our fluid, the gas constant for the specific fluid, and then temperature we're working with. And we have all that stuff up here, right? Standard atmospheric pressure. This is going to be for standard air. Um, and then we have a temperature given. So we're solving for this density here because we don't know what the density of this specific fluid is necessarily. So we'll solve for that there. So doing that over here. So standard atmospheric pressure is 14.7. And we're going to multiply that by 144 to get that in pounds per foot squared. So we get our density in a unit that we can work with. And then our R value, you'll look this up either in your textbook or online, something like that. And then the temperature we can use isn't 200 degrees Fahrenheit. This temperature should be in Rankine, which is to Fahrenheit as Kelvin is to Celsius. So to do that conversion, you just add 460. All right. So for your rho, or your density, you get 0.00187. And so we can plug that back in over here. And so we have Q is equal to m dot over rho G. And then we get 1.33 feet cubed per second. Do a little division there. Alrighty. So then we can take this, plug this in up here. We have a rho, and then we have a viscosity based on standard atmosphere, or sorry, standard air. So we can get that. 1 second. 1.33 is equal to 2100 times pi. Our viscosity is 4.49 times 10 to the negative 7th. We're looking for that diameter over 4 times this density that we found over here, 0.00187. Do a little bit of algebra or have your calculator do it for you, and you should get the diameter 3.36 feet. Cool. So what you'll start to notice about at least this first part of flow in pipe problems is that it's pretty plug and chug. But the problem is, I'll write this down here real quick. Whoop, that wasn't even close to spine, right? Plug and chug problems. So some of the issues that we'll run into here is, what do we plug into? Right? What we've kind of developed in this semester is like a toolbox of formulas that you'll see. So like ideal gas constant, I bet you forgot that we even went over that this semester. But again, it comes back over here so we can find the density that we're going to use in our Reynolds number. The next thing is what do we chug? Like what are the numbers we put in? So if we're looking at, for instance, this this Reynolds number here, we can't use the standard density that is given in maybe a table or something like that, because that's probably not at 200 degrees Fahrenheit. If we could find a density or viscosity at that point, that would make sense. But we'll use the ideal gas constant to kind of gauge our densities. Viscosities you should be able to find in a chart, though. Also, the density kind of varied with this mass flow rate that we have, so that makes a difference there. We also have continuity equation. That's another thing that you might have to plug into. Um, so there's a lot of different equations that might come back up in these sorts of problems, but the one that will always be there is this Reynolds number expression here. And that's going to kind of differ whether or not that's going to be turbulent or laminar, and you're going to want to remember those ranges. Um, yeah, Dr. Schaefer, I think, mentioned those in his lecture, so you can go back and look at that if you need. Um, but than that, if you want to see more problems like this, again, WebEx, find me on WebEx. Come ask questions or just sit there and we can work through problems. And if anything's confusing, you can stop me and ask. Can't really do that in this format. So, um, yeah, I hope to see you in WebEx meetings. But until then, see ya.